What I wanted to look at with this one is the weight force at the equator. Now, when you are sitting at the equator, we'll sort of look down on the world as if we're looking down from the pole. So if that's the North Pole. So a person, we'll put them up this way because it looks a bit easier, is at the equator. They're obviously a lot bigger than they would be in real life. So that person is spinning round. And the speed they're spinning around at, v, is just the distance divided by the time, right? The distance being the circumference, which should be 2 pi r, divided by the time it takes for them to spin round. And to go around the world once is 24 hours times 3,600 seconds, right? So we could calculate that velocity. But the thing is here, and we're not necessarily going to do all the calculations, the velocity requires, to go in a circle like that, you need a centripetal force, and that centripetal force is equal to v squared over r times m. So that's the centripetal force needed, and we're all pretty good now, and we probably know that that comes from gravity acting on the person, or their weight force. So v squared m over r comes from their weight force, which their weight force is equal to mg. Now, if part of that weight force is being used to keep them going in a circle, then part of it is not actually being used to pull them into the ground. So the reaction force against that weight force is going to be smaller than just their true weight force, because part of their weight force is providing the centripetal force. So if we calculate that centripetal force, right, then we can say that the reaction force on the ground, and that's what gives you the reading on scales. So the weight force at the equator might really be what it normally is, but we would have to actually subtract this force away. So mg, the reaction force, is going to be their weight force minus the component of the weight force, v squared over r times m, that is being used to keep them going in a circle. And obviously we would just need to substitute that v into this equation, and we would get it. Then we could get their readings on the scales. It would be in newtons, and we could do the whole divide by 9.8 and find out how many kilograms their scale is going to read. So we can say basically from this, though, that your reading on the scales, if we put scales there underneath the person, is going to be less at the equator, because at the equator your velocity here is biggest, which means you need a bigger component of your weight force providing the centripetal force. If you're standing on the pole, you're not going in a circle at all, your reading will be what it should be.